Okay, so in this video I'll introduce the concept of submodules and quotients, and quotient modules. So I'll begin with the notion of a submodule. So definition, let R be a ring, or like Bas says, let R be an object in the category of rings. And M an R module, so a left R module, maybe I write it a left R module, then a left R submodule of M, so let's call it N, is a subgroup M such that it is closed under the multiplication by R. So for all R in R, and all N in N, we have that R times N is still in N. Okay, so that's a submodule, so it's very similar to a subvector space that we know from linear algebra. Some examples. So let me begin with the trivial examples. So again, I have R ring and M an R module. Then we have the trivial modules. So unless M is the zero module, you have two of them, namely just the subset which only contains the zero of M, and the other one is M itself, right, which is a subset of itself. Okay, so these are two very basic examples. Recall in one of the previous videos I said that actually any ring is a module over itself, so you can just multiply, use the multiplication of the ring to make the module structure. So if you use this definition, then submodules become ideals. So let I in R be a subset, then I is a, so I should say left R ideal if and only if I is a left R submodule. Okay, then if we have a morphism of R modules, we can also attach two submodules to it. So suppose let f from M to M prime be a morphism of R modules. So R still a ring, and then the kernel F is the set of all x in M such that f 0. So this is a R submodule. So left one of M. And I can also, of course, look at the image. So this is so this one we call the kernel, right? Kernel of F. And we also have the image of F, which is given by well, all things, we write it like this, all things in n prime, which come from M. This, and this is an image of F. It's an R submodule. And primed. Okay. So these are some examples of submodules. Of course, you can make many of them. So let me find the eraser. So last class of examples are like when you have a submodule and you take the, or sorry, the subset, and you take the submodule generated by this subset, right? So if you have a subset of any subset E in M, we can consider okay, let me just say that E, sorry. Let E in M be a subset. And then our submodule brackets E are generated by E is our submodule of M generated by E is the smallest submodule, our submodule of M that contains E. So equivalently, this thing E R is what? Well, it's the set of all combinations that you can form using elements of E. So the set of all finite sums, I is 1 to R, Ri, Ei, where and Ri to Rn, R, and Ei to En, so it's very easy to see that this is again an R module. It's closed under the operations, and it is the smallest submodule that is going to contain this subset. Okay, so So give a definition that's going to be useful later on. So definition, we say that an R module M is finitely generated if there exists some finite subset E in M such that E R is equal to M. Okay, so some example. I gave already some other examples, of course, of submodules, but one example could be, for instance, let E be equal to 1 and I. So with I mean just a choice of a square root of -1, so some subset of C, complex numbers, and then I can take E, the module, the sub, so the complex modules, it's an abelian group, so it's a Z module, so I can take the Z module generated by these two elements, so that's going to be, of course, the set of all complex numbers, A plus Bi, where A and B lie in Z. Yeah, so this is a finitely generated R module, a Z module, because I can generate it by two elements. So in fact, so this thing is often denoted as Zi, just because it's basically linear combinations of 1 and i's with coefficients in Z. So this is a more common notation. And as it turns out, this is actually a ring, and it's called the ring of Gaussian integers. So Gaussian integers. Of course, you can make as many examples as you want. Okay, so the next topic I want to discuss are quotients of modules. So let me erase the blackboard. Quotients. So what is a quotient? So for this, I start with R, a ring, and I let M be, so let R be a ring, and M an R module, and N and M R submodule. Like that. So now we can ask, can we make a quotient of M modulo N? So we define the quotient. So just as with the abelian groups, so the quotient module N by N is, so the R module whose underlying group is just M modulo N, the quotient of the two abelian groups, and the following multiplication, so where this dot is defined by the following map, so go from R cross M modulo N to M modulo N, and I send a pair R comma M plus N to R times M plus N. Okay, so this is the definition. So here you would have to check that this map is well defined. So, because what I did when I wrote this down is implicitly I chose for my n coset in M, I chose a representative M here, and I mapped my coset to the coset with representative R times M. So what you have to check is that this is independent of my representative. The point is, of course, that if I had chosen a different representative, then this is just the old one plus something in N. So whatever the result is, it's going to differ by R times something in N. But since N is stable by R multiplication, that difference is not going to matter modulo N. Yeah, so that's why this is a well-defined map. Okay, so this is a definition, but what is actually much more important is the universal property of the quotient. So, universal property. This says that for all R modules T and all R morphisms from F from M to T such that F of N is 0. So I have some diagram. So M goes to T via F. Here I have my quotient, right, where I just send an element M in M to M plus N. This way, there exists a unique map let's call it F bar from M mod N to T such that F bar, so let's call this map here Q, such that F is equal to F bar equals to Q. So in the diagram I'm asking that there exists a unique map here called F bar that makes this diagram commute. So actually, this universal property is so strong that it characterizes M modulo N up to unique isomorphism. So what you could actually do, and some would argue that this is maybe actually better, is to take this just as a definition for what the quotient is, and push this construction more to the background, where you only use this construction to show that the quotients exist. Okay. So this universal property is one thing that I didn't do is this this proposition that m mod n plus m dot, as I defined over there, satisfies the universal property. Okay, so in the proof, I'm going to skip it. So it's again using the definitions. So an example quotient. So if I take S1 in C, the unit circle, and I take the exponential mapping. So consider exponential mapping from R to S1 by sending a real number to the exponential of 2 pi I times R, like this. Then S1 together with this exponential map is quotient of Z in R. So by which I mean this pair satisfies the universal property.
So here the ring R is the integers, right?
Yeah. Oh, yeah. So here I think in terms of R modules.
Z modules.
Z modules. Okay, so maybe I just write it here. This argument is taking place in the category Z modules, right? So the circle is a Z module, complex numbers is a Z module.
No, that's not. I mean, C star. And if you want to multiply.
Oh, yes, you're right.
Yeah, that's actually better. Right?
Yeah. So C star is a Z module if you use the multiplication. And then this inclusion here is an inclusion of Z modules. And the circle is the quotient of R by Z. Okay. So this is what I wanted to say about quotients. So then comes the last part of the video, where I discuss the isomorphism theorem.
So 6.5 minutes.
Okay, so I'll do it. Try to do it.
Oh, you don't need to rush.
Okay, so. So what does this say? So let R be a ring. And F from N to M prime. The morphism between two arbitrary fixed R modules. R morphism. So that's A R morphism. Then the theorem says that I get so recall that when you have an R module morphism, associated to it, we had the kernel of this module morphism, and that was a submodule of M. So what I can do now by this quotient is I can take the quotient of M by this kernel, and I get some induced morphism. Right, so I get an F bar coming from M modulo the kernel, and what it will hit will still be the same as the image of F. And the point is, since I've modeled out by everything that's going to 0, this new map will have a trivial kernel. So the theorem is saying that this induced mapping is an isomorphism of R modules. Okay, so maybe, actually I want to say the mapping M goes to M plus F is an isomorphism of R modules. Okay, so finally, let me just define co-kernels. So, definition. The co-kernel of a morphism F from M to M prime between two R modules is the quotient of M primed by the image of F. Right? Recall that at the beginning I said that the image of a morphism is a submodule of the codomain, so it makes sense to construct the quotient of M prime by this image. So we write co-ker of F. So this is by what I wrote here, equal to M prime mod image of F. So now if you go back to these lectures of Stefan, he talked about AP and monomorphisms, and he explained actually that in the category of K vector spaces, apimorphisms and monomorphisms correspond to surjections and injections. So you can actually repeat what he said now in the category of R modules, and you get that, again, these are just surjections and injections. So in the category of R modules, monomorphisms, and apimorphisms are injections, are precisely the injections and surjections. Okay, so and if you look at this proof, you see that somehow the crucial thing to use is this notion of co-kernel and kernel to prove these two facts. So now that I have introduced them, you see that you precisely have what you need. Okay, that's it.